Recall that in our last video, we looked at the Yule-Walker estimation technique in order to estimate the parameters of an ARP model. In this video, we'll look at the least squares estimation technique. Now to start, we'll first of all consider the ARP model given by this form. The general form is x sub t equals phi1 times x sub t minus 1 plus phi2 times x sub t minus 2 all the way out to phi p times x sub t minus p plus a sub t. Now, at first glance at this formula, it looks like our general regression model. But remember that things are quite a bit different in this time series setting because we know that these independent variables, xt sub 1, xt minus 2, out to xt minus p, are really lagged versions of the dependent variable. And that's not the case, of course, in the general regression setting. But still, it's very instructive to think of this as a regression model because what we're wanting to do in this video is estimate the parameters phi1, phi2 to phi p, and the way we do that is the very same strategy as we use to estimate the parameters in the general regression setting. That is, we want to minimize the sums of squares of errors, which is given by this a sub t term. So our next thing I want to do is let's try to write out some terms. Let's let t be 1. And when we do that, we run into trouble right away because we see that x sub 1 equals phi1 times x sub 1 minus 1. Well, that's x sub 0, and we don't have the data point x sub 0. We start at x1, then x2, all the way out to xn, so we don't have this term. And even when you go to x2, you run into the same issue because it's not the first term that would trip us up, but it's the second one because that would say xt minus 2, and 2 minus 2 is 0. So we can't do that. The first place that we can actually start is x sub p plus 1, which is given by phi1 times xp plus all the way out to phi p times x1 plus a sub p plus 1. The next term, x sub p plus 2, equals phi1 times x sub p plus 1 plus all the way out to phi p times x2 plus a sub p plus 2. And that continues on until we get to x sub n equals phi1 times x sub n minus 1 plus, that goes out to phi p times x sub n minus p plus a sub n. And there is our system of equations. Now, in this system of equations, again, the goal, we're trying to find the optimal phi1, phi2 to phi p. And the way we're going to do that, as we said, we're going to try to minimize the sums of squares of errors. That means we're trying to minimize the sums of squares of these a's. As far as notation, I'm going to write this as S sub C. C stands for conditional. This was written up in the book, started from the derivation of just the standard regression setting. So we've seen this before, this notation before. So S sub C equals the sum of a hat t squared, so we're summing the squares of these, and t goes from p plus 1 to n. Okay, now another way we can write that is the sum from t equals p plus 1 to n, if we're trying to solve for a of p plus 1, we could pull all of the phi terms to the left side. So when we do that, we get the following: x sub t minus phi 1 hat. Why hat? Well, because we need to estimate those. So whenever we pull that over, we're going to make the estimation. So phi hat 1 times x sub t minus 1 plus phi hat 2 times xt minus 2, all the way out till we get to phi hat p times x sub t minus p squared. So that's what we're trying to minimize, is this term right here. Now remember how this is done back to calculus days. The first derivative test says to do what? Well, take the first derivative, set it equal to 0, and that's how you find the local extrema, right, whether it's the min or the max. And that's exactly how this is done. Now in practice, we're not going to be doing that. We're going to let software do it for us, but that's where that's coming from. Okay, that's good to know. All right, so this is really the strategy behind the least squares estimates. And remember, we talked in the video about the Yule-Walker estimates, and we'll say it again for the Berg estimates, that the gold standard is the least squares estimate. So this is a great estimation technique. Now, there is a problem or a drawback, and that is the fact that we're nearly ignoring some information. And of course, as statisticians, we hate to throw away data, and we're really guilty of that in this case. We're nearly ignoring x1, x2, all the way to xp. Why do we say that? Well, let's go back over here and look. We see x1 showing up here, and of course xp's here. But as we move down, we don't use those again. Okay, so we're not using those values x1, x2 to xp very often, and so it's almost like we're wasting information. Now, it is true that we use things like xp plus 1 and xp plus 2, data values in that area, we use those quite a lot. But we're just not taking advantage of x1, x2 to xp. So that is one of the drawbacks of the least squares method. I mentioned the word Berg just a bit ago. That's going to be our third estimation technique, which we've not discussed yet. But the Berg estimation technique serves as a compromise, and Berg took advantage of the fact that, well, it's nice that we're using this information from p plus 1 to n, but it'd also be nice to take advantage of the information from 1 to up to p as well. And that's what's going to happen when we talk about the Berg estimation technique.